Hi everyone, in this module we're going to really dive into quadratic functions. So we're going to talk about how to graph a quadratic function in the two different forms, as well as what purposes the two different forms represent. So in this video we're going to go through how to find the vertex of a quadratic function along with its intercepts, and I'm going to even throw in domain and range. So there is a decent amount of information based on just quadratic functions, and I think it deserves its own video. So let's start off with what is a quadratic function. So your base function is always going to look like x squared. Now remember, when you square something, that's the same as saying it times itself. So let's develop a general idea on what these graphs will look like. So if I take -2 squared, if I do -2 times -2, I get the value +4. If I do the same thing with -1, -1 times -1 gets me +1. 0 times 0 is 0, and 1 times 1 is 1, and 2 times 2 is 4. So we get something like this. If I plot these as x and y coordinate points, 0, 0, 1, 1, 2, 4, -1, 1, and then -2, 4. I get this generic shape, which is kind of a U-shaped graph, which is also referred to as a parabola. Now, these have unique properties. The first thing is that their domain is generally bracket 0. Their domain is -infinity to +infinity. This will never change. I was doing the range there. And now let's actually move on to the range. So the range is from 0 to infinity. Now, this value is at a location called the vertex, which is the center of the graph. So you see right here at the center, basically if I was to split this graph down the center, it actually creates sort of an illusion, not an illusion, but a mirror image on both sides. This line going through the vertex is called the axis of symmetry. And these are all important terms for this particular graph. So you want to have that the axis of symmetry is the line through the vertex. So let's actually see what happens with these graphs. Now, if you notice, I've got x squared and then a +2. So basically, we already created these four coordinates. If you remember, the first one was -2 times -2 is 4, -1 times -1 is 1, 0 times 0 is 0, 1 times 1 is 1, and 2 times 2 is 4. Well, if I take all these coordinates and I add 2 to them, I end up with these new coordinate points. So this would be 6, 3, 2, 3, and 6. So let's plot these coordinate points. So -2 and +6, -1 and +3, 0, 2, 1, 3, and 2, 6. And you can see that again, we get this quadratic parabola shape. The vertex of the graph is not at 0, 0 anymore, but it's now at the coordinate 0, 2. And my axis of symmetry is still in the same location, right down the center. So I'm going to abbreviate the word axis of symmetry as AOS. And the way that we write this line, even though we just talked about how it always goes through the vertex, is we would say it's the x equals value of the vertex. So in this case, we would say that the axis of symmetry would be 0. Now, this is everything for this transformation, but if you notice, what did that +2 do? It moved the graph up by 2. And so a really common question to be able to answer now is, let's say if it was a -2, it should make sense that instead of moving the graph up 2, it would actually move the ground down by 2. So if I had the equation x squared minus 2, what I would expect to happen is instead of the coordinate being 4, 1, 0, 1, and 4, I would take those coordinates. So I have my x coordinates the same every time. 4, 1, 0, 1, 4. And I would subtract 2 from them. And so I would get something like 2, -1, -2, -1, and 2. And so if I was graphing that, this is what it would look like. So one thing to point out about this, same style graph, just move down, same axis of symmetry. But I hope it makes sense that if you have x squared plus a number, it just takes that U shape and moves it up. If you have it minus a number, it moves it down. Now what happens on the inside? Now this is kind of a unique special thing that happens. And so let's plug in these points directly and actually see what happens. So if I plug in -2 and I square this, I get basically -5 squared, which is 25. That's going to be really hard for us to graph. Let's do -1 minus 3 squared. That gets me -4 squared. That gets me 16. Still going to be tough to graph. Let's plug in 0. -3 squared would be 9. Let's plug in 1. That would be -1 squared, which would be 1. And, oh, I'm sorry. That should be -2 squared. So 4. And if I plug in 2, I get -1 squared, which is 1. And it's like, wow, what is going on with this graph? There's not a lot happening here. And when I go to plot, let's just plot these 3 points for the time being, because there's really not much else we can do. So my first coordinate point is 0, 9. My next is 1, 4. And my next is 2, 1. Now, if you recall, we had that sort of parabola-like shape, a U, and I don't really see it here. So I might have to keep going. So let's plug in 3, and let's see what happens. So I get 0 squared, so I get 3, 0. And if I plug in 4, I get 4 minus 3, which would be 1. Oh, wait a minute. And if I plug in 5, I get 5 minus 3 squared, I get 4. And if you look at that, I see that U shape now. And so what happened is, when you have something inside with x, it moves the opposite way. Left or right. The previous one was up and down. So since this was a -3, it actually moved the graph 3 to the right. So again, here's my vertex. Though previously the vertex was 0, 0, but it got shifted 3 to the right. So now it's 3, 0. And again, that axis of symmetry still exists, but it no longer exists at 0, right? If that's not dividing this graph in half. So the coordinate point that we would want to go through is my vertex. And so that would give me the axis of symmetry equation, 3, 0. So each of these graphs do their own sort of transformation. Now again, without having to do a lot of work, let's speculate what might happen if I had x plus 5 squared. So if -3 moved it 3 to the right, it should make sense that plus 5 actually will move it 5 to the left. So instead of my vertex being at 3, 0, my vertex is at -5, 0. And I'm just going to draw in some supporting points here. And boom, that's my vertex. Now we have a 1/4 factor in front. So what this is going to do is this is what we call a vertical stretch or shrink. Now, it's called a shrink if the number you're multiplying is less than 1. So for example, I have everything multiplied by 1/4. So let's go through this process. 1/4 times -2 squared. That's just 1. 1/4 of -1 squared. That's 1/4. 1/4 of 0 squared. That's still 0. And 1/4 of 1 squared. That's 1/4. 1/4 of 2 squared. That's 1. And so if I plot those points, 0, 0, 1, 1/4, and 2, 1, you can see this graph didn't really get bigger, it just kind of shrinks towards the y-axis. Sometimes we call this a compression too. There's a lot of different ways to phrase it. But in general, you want to realize that basically the graph will get wider in this sense. And with a stretch, the graph will get more narrow. So let me take, for example, let's say I didn't do 1/4. Let's say I did 2x squared. If I plug in these x coordinates and evaluate, I get the coordinate points 8, 2, 0, 2, and 8. So you can plug them into this equation and see that you get those. But this is what that graph would look like. 2, 1, oh, whoopsie, that should be here. And if you can see, it's a much more narrow graph as before. So when we have a number out front, it actually controls how wide or how narrow that graph might be. The larger the number is, the more narrow the graph becomes. The closer the number is to 0 you multiply by, the flatter it starts to kind of spread out. And our last transformation that we'll talk about in this part is a negative. Now this is what we call the flip over the x-axis. So if I take my -2, my coordinate becomes -4. If I plug in -1, my answer ends up being 1, -1, back to -4. And if I plot those points, -1, -1, 1, 1, 2, -4, -2, -4, I get my graph to go this way. So again, vertex, like the previous one, is unaffected. It did not get moved around, which also means the axis of symmetry does not change. Now what will change in this is the range. Now remember, we talked about domain and range in 10.1. Domain is all the x coordinates from left to right. So this graph goes left and right forever still, but the range has now been modified because the graph no longer goes up forever. It starts from the bottom. It starts from -infinity now, and then we'll go all the way up to 0. So when you have this flip, it actually switches your range, which is kind of important to the overall shape of the graph. So let's kind of just recap everything, just so you have it all nicely compiled. If you have a plus c on the outside, this moves the graph up if it's a plus c, and moves the graph down if it's a minus c. This is going to impact the y-coordinate of vertex, and it's going to impact your range. If you have a plus c on the inside, it's actually going to move to the right if it's a minus c, and it's going to move it to the left if it's a plus c. It does the opposite. This is the tricky one for a lot of people. What this is going to do is it's going to impact the x-coordinate of your vertex. It's not really going to do anything to your domain because your domain always changes, so you don't have to worry too much about that. The c value makes the graph more narrow if c is greater than 1, and wider if c is in between 0 and 1. We can't count 1 because 1 doesn't do anything, and we can't count 0 because 0 will basically eliminate the graph. Okay, so in this case, more narrow means like this. Wider would mean something like this. And then finally, the negative, this is going to be the flip over the x-axis. This is going to entirely change range. It's now going to go from -infinity to a number. So these are just some of the general impacts that these have. this is really good to have as sort of a general basis as you're like working through some of these problems. So let's talk about how we can do all of this and throw in some pieces together. Now for my x-intercepts and y-intercepts, I may estimate. I will show you how to find them, but they're not always super easy. So let's talk about the transformations first. The first thing is we have a transformation that's going left and right. So we know that this is going to be the opposite of the inside. So this means it's going to be 4 to the left, and the graph is going to flip upside down. So this is how I want you to handle this. You start off with where your center should be, which is always 0, 0. I'm going to shift my center 4 to the left. 1, 2, 3, 4. Whoops. That would be right here. Once I shifted it 4 to the left, this is my new center. So this is my vertex. That vertex is now -4, 0. Since the graph has been flipped, I'm going to go and get 2 more points. In general, you can use this number in front as your slope. So I'm going to go down 1, over 1 in each direction. I call those my anchor points. And this will be my U-shaped graph going down. And that's really all I need to put for this graph. Now let's fill in domain and range. So domain is the free answer every time, negative to positive infinity. That never changes. Now my range. The graph starts at negative infinity. It's down below here. And it's going to go all the way up until it hits its highest point. Now, a lot of people think the highest point is -4, except when we talk about range, we exclusively talk about y values. So its highest point is actually 0, because in terms of the y-axis, that's the highest it gets. Now, my x-intercept is good because my x-intercept is just here on my x-axis. So that's -4, 0. And we've talked about finding the y-intercept before. It's not on our graph, but remember the y-intercept is when x equals 0. So let's plug in 0 here. 0 plus 4 squared. 0 plus 4 is 4. 4 squared is 16. Negative. So we now have both the x-coordinate and the y-coordinate of my intercept. So my intercept for my y-axis would be 0, -16. So I hope that's made a little bit of sense. So let's try another one. And again, might be helpful for you to pause and try to work out some of these pieces on your own at this point, and then we'll kind of go through what we might look for. So I always like to figure out my transformation. So again, we normally start at the center. And let's discuss what's happening. So in -3, remember inside is the opposite. So this goes 3 to the right, and the +5 goes 5 up. So if I slide my coordinate from the center over 1, 2, 3, and up 5, I'm at this coordinate point, 3, 5. Now, I am flipped over the x-axis, which means to get my coordinate points, I just follow going down 1, over 1 on each side. Now, before I go any further, it might be helpful to get the intercepts. Now, the only intercept I really might want to use here is my y-intercept. So again, the y-intercept occurs when x equals 0. So if I plug in 0 for x, I get -9 plus 5, which would be -4. So that would be my y-intercept here. And you can see that that's a pretty good way to get this graph. Now we do have x-intercepts, and for right now, we're just going to guesstimate them. We'll talk in more detail how to solve for these. But my x-intercepts might be something like negative or positive 0.5. 0 and 4.50. So that's really all we need for the graph. My domain is negative to positive infinity. My range, again, starts from the lowest to the highest, y value, which from the y-axis as a ruler would be 5. So again, let's talk about the transformations. I'm actually going to change this one. We've done 2 negatives in a row. Let's make it a positive. And let's do a positive example. So this graph has just been shifted up 1 and is more narrow. So we have 0, 0. It gets moved up by 1. So my vertex is at the point 0, 1. And so, again, I can use this as sort of my slope. So instead of going over 1, up 1, I go up 2, over 1. And boom, just like that, we have the shape of my graph. The good news is it's already touching the y-axis at 0, 1. And if you look, there is no x-intercepts. So all we really have to do is do the domain and the range. So domain is negative to positive infinity. My range is 1 to infinity. Okay, so that's basically everything that there is to these types of graphs. Again, we still do have the axis of symmetry in this problem here. That would be x equals 0 since the graph didn't move left or right. All right, and so let's do another example. So let's do our little shift here first. So 0, 0. And since it's inside, it's going to do opposite. So it's going to go 2, 0. So we move 2 to the right. We know this graph is going to be wider. What might be helpful here is to get the x-intercept, and that might, or the y-intercept, and that might help us give us a little bit easier way to get an extra point. So if I plug in 0 for x and solve, I get 1/4 times negative 2 squared, which gets me 1. So these are my 2 points to use, 2, 0, 0, 1. And so we can kind of look right here. If I went up 1 over 2 to get that y-intercept, I can go up 1 over 2 the other direction. So you can already see that this graph is, in fact, wider. Now, we actually already have the x-intercept. It crosses at its vertex. We also have my line of symmetry, my axis of symmetry here. Now, since the axis of symmetry has moved with the vertex, we would say it's x equals 2. So whatever that axis of symmetry number is just your x-coordinate for your vertex. Your domain is negative to positive infinity, as always. Your range, since it didn't move up or down, is 0 to infinity. So that's really it for these transformations. It's applying a bunch of the concepts of the transformations to each other. Now there are 2 forms of the equation. There is what we just did, which was vertex form. And the new one that we can talk about is standard form. So vertex form looks generally like this. Y equals a times x minus k squared plus h. This is your vertex form. The reason it's called vertex form is these 2 k and h's actually give you the vertex of the equation. Opposite, so of k, same as h. In standard form, we don't have access to the vertex. It's not easy to get the vertex. What it does give us access to is factoring, and this is a lot easier for the x-intercepts. That's actually why we like this form, which is nice. So let's make sure we understand how to figure out like what these components are. So if you look, we have a x squared plus bx plus c. A is your value that's in front of x squared. B is your value that's in front of x. And c is your constant. Real quick, a common mistake is that people include x squared and x in their a and their b. It is not a and b. It is the indicator of a and b. Just like how the number in front of x for a function is its slope normally, x is not the slope, it's the indicator. What this does give us, though, is there is a formula to get the vertex from standard form. So instead of just knowing the transformations, we can follow this formula. X equals negative b over 2a. Once you get this number, you need to plug back in because this gets you x, and every coordinate has a x and a y. So when you plug that x number back in, you get the y value. So let's graph this using the vertex. So we want to use the vertex equation, negative b over 2a. So let's figure out my a, my b, and my c. So when I plug in negative b, I get, I do it up to the side here, negative 2 over 2 times 4. So that's 2 over 8, and that's 1/4. So this is not going to be a really pretty number here. Now, that just gives me x, so we have to now plug in 1/4 into the big equation that we have there. So we're going to do 4 times 1/4 squared minus 2 times 1/4 minus 6. So 1/4 squared is 1/16 times 4. That gets me another 1/4. Minus 2 times 1/4 is minus 1/2 minus 6. A little bit of a crazy value here, but when we do all of this together, we get the decimal negative 6.25. And a decimal is fine here since we're graphing. So my vertex is 1/4 and negative 6.25. Now I'm going to rewrite this in terms of all decimals, so 0.25 and 6.25. So that's my vertex. So 0.25 and positive 6.25. So 1, 2, 3, 4, 5, 6. It's going to be kind of about here. If you put it, on 6 or a little bit closer to 0, that's fine. Now again, one really helpful thing here is to find my x-intercept. This is always pretty easy, so that's when x equals 0. What's nice about standard form is there's a lot less work. So 4 times 0 squared minus 2 times 0 minus 6 gets me negative 6. And so my y-intercept is 0, negative 6. Oh, that should be negative 6.25. I was like, something is off with my vertex. Sorry about that. Let's move this to the right spot. And right there. And so now it's really tight, but we can actually graph it this way. And we can see that my parabola is kind of narrow, which should make some sense because that number in front is larger than 1, so it should be a pretty narrow graph. My domain is negative infinity to positive infinity. My range, the lowest the graph go, is the y-coordinate, so negative 6.25, and it goes up forever. Now with our x-intercepts, we're going to guesstimate these again. It looks like my x-intercepts are approximately negative 1, 0 to 2, 0. Again, when we do one that's a little bit more factorable and easy to solve, then we will actually kind of be able to find these intercepts. But for right now, we're just kind of looking at where the graph seems to be headed. Now, this would be an example in which we can try to find as many pieces as possible. So, my vertex, negative b over 2a, the only thing is, this is a, and since there's no value, no variable, this is c. So where's my b? So in this case, since there's no x, that means b equals 0, which is going to make this vertex equation very easy to work with. So when I find my x, I get x equals 0 divided by, negative 0 divided by 2 times negative 5. Well, positive and negative 0 are the same thing, so I'm going to change that to positive 0. 2 times negative 5 is negative 10. So my x-coordinate is 0. And my vertex, well, when I plug it back in, I get negative 5 times 0 squared plus 10, which is 10. So my vertex is at the coordinate point 0, 10. Now for my slope, I have -5. So a quick way for me to try to figure this out is to go down 5 over 1. To get my y-intercept, I plug in 0 for x, which we actually already did, so I don't really have to do work here. Now to get the x-intercept, that's when y equals 0. So we got to do 0 equals -5x squared plus 10. And I solve for x, so I minus 10 on both sides. -10 equals -5x squared. Divide both sides by -5. I get x squared equals 2, which is not normal and easy to solve. So what we do is we take the square root on both sides. And we actually end up with two answers. X equals plus and minus the square root of 2. If you put that into your calculator, you get 1.7 and -1.7. Which means I actually have two x-intercepts. Positive 1.70 and -1.70. And so that would be the overall shape of the graph, which, again, you don't really need the x-intercepts at this point to know what the shape would look like using all these other pieces. So my domain is -infinity to +infinity, and my range is -infinity to bracketed 10. So, this is really how we just solve all these problems. So let's do one more kind of quick one. Even though a is a little bit of annoying mess here because of the fraction, it still shouldn't be too crazy. So -b over 2a. So let's find my vertex first. So -1 over 2 times -1/4. So this becomes 1 over -1/2. Now this looks really bad, but one thing I want to do is get rid of a denominator with a 2. So a little trick I use is multiply by 2. Whatever I do to the denominator, I have to do to the numerator. And when I do this, I get 2 up top and -1 down the bottom. So this is a way for me to eliminate a denominator without having to do a lot of math. So my x-coordinate is -2. And so again, we got to plug in -2 to get the y. So my y-coordinate would be -1/4 times -2 squared minus -2 plus 8. So -1/4 times 4. This is a +2 and a +8. I get -1 plus 2 plus 8, and that finally gets me 9. So my vertex is -2, 9. Which, oh good, I do have space for -2, 9. Right about there. I like to get my y-intercept, which is actually quite easy again. Remember, it's when x equals 0, so 1/4 times 0 squared minus 0 plus 8. Well, that's 0 minus 0 plus 8, so just 8. So 0, 8. And right from here, we can already see that from the vertex, it goes down 1 over 2. So if I just go the other direction, I have enough space to graph. And based on where I think my intercepts might be for x, it might be 4 and 9. Or -9. So domain, -infinity to +infinity. My range, -infinity, the highest the graph goes is 9. So that's really it for this. These still have the axis of symmetry. This one is shifted again, so my axis of symmetry is x equals -2. And so just a recap on the difference between these. Vertex form has your vertex at k and h. It's the transformation inside and outside. It can be converted if we distribute. We're not really going to do a lot of conversion back and forth, but it is possible. Whereas in standard form, intercept is just the C value. If you go back through and you realize that when we plug in 0 and 0, this is always my y-intercept. I don't have to do any calculations once I see this pattern, but we still can find the vertex with a little bit more work. Now, the reason why we care about the vertex in the first place is a lot of times we want to minimize or maximize profit or some value. Maybe it's minimizing a cost of something. Well, that would be when we find the vertex. So that is your min and max. So more often than not, that is what we want to identify because the equation requires us to do different things. So for example, a ball is thrown up in the air and is modeled by this equation. So a couple things we know. The graph opens down. The graph has been shifted 4 to the right and 22 up. So we know that my graph would look something like this. Here's 4, here's 22. That's my vertex. And so you can kind of see this is the motion that the ball is being used, where it gets thrown up into the air and begins to come back down due to gravity. So this point is the highest point in the graph. So when does the function hit the highest point? When is just the x value. So we would say when x equals 4. What is the ball's maximum height? That would be the y value. So that would be y equals 22. And finally, what is the starting height of the ball when it's being thrown? For this, it's not very clear right off the bat, but if we're talking about a time that starts, that would be when x equals 0. Well, the important point is the y-intercept at that point. So let's plug in 0 and see what we get. Negative 4 squared plus 22. So 0 minus 4 is negative 4. Negative 4 squared is 16. And so my answer is 6. So that means the starting height is 6 feet. Now in this one, let's say a set of dough expands with its yeast rising and replicating, similar to a quadratic equation where it rises over time but begins to decrease. So this is in standard form. So we don't really know where the vertex is, but based on the context of the equation, it rises over time and begins to decrease. T, let's change that to x, and B, let's change that to y, is sort of the number of bacteria versus time. So when does the dough have the maximum number of bacteria? So again, the when question is the vertex of x. I don't know where that is, but we have an equation for that. Negative b over 2a. B is 8. A is negative 2. So I get negative 8 over 2 times negative 2. So when x is 2, and since x is in hours, we can say 2 hours. What amount of bacteria? Well, that would be the y value when we're at its maximum. So when x is 2. So we can just plug in y equals negative 2 times 2 squared plus 8 times 2 plus 32. So I get negative 2 times 4 plus 16 plus 32. And so the initial bacteria count at that point would just be 40, let's say bacteria cells. I think that would be the best way to phrase this. And then finally, what is the amount of time when you started keeping track? So again, instead of at its highest point, this would be when x just starts. So I get 0 squared plus 8 times 0 plus 32. And so again, if you notice, it's just that number at the end. So 32 bacteria cells. Okay, so that's all of our information on quadratic equations. I hope that was helpful, and I'll see you in the next video about radical graphs.